Alright, so now that we have seen how the parallel loops generally operate and how to cancel them or break out of them and all sorts of things, we're going to look at how to partition those loops. Now, when you do a parallel for, what really happens is you effectively split the overall range of values. You split it in a certain number of chunks, and then those chunks get taken care of by these separate threads. Unfortunately, this can become rather inefficient. So in this example, we're going to do something a bit more complicated. Instead of just outputting some values, I'm actually going to benchmark my code. So let me go into the Nugget Manager and we'll get benchmark.net to do it for us. All right, so benchmark should be fairly quick. Okay, so we want benchmark.net. Let's go again. Okay, so I'm going to install it. Okay, so we now have the package. Let's go back into our main function. What I'm going to do is I'm going to benchmark a chunk of code. So I'm going to have a very simple function called square each value. Now let's suppose that we want to just take a bunch of values and we want to calculate the square of each of those values. So we'll have a count, let's say 100,000, and then what we're going to do is we'll take the values. So I'll say var values equals enumerable.range, and we'll make a range from 0 to count. So we'll make this many values, and then we'll have a placeholder for the results. So I'll just have an array. Results equals new int with count, and then in parallel I want to take each of the values which go from 0 to 100,000 minus 1, as this range suggests, and I want to take each of those values, I want to square the value and then write it to the results array. So you might write something like the following: parallel.for each, provide the values, and then for each of the values I say that the results at this particular value is equal to math.pow. Let's do it slightly inefficiently, so I want to square it by using math.pow with an argument value of 2. So you need a cast in here, and this is it. Now this might look like it's a sensible kind of method, but in actual fact it's not very useful. And the reason why it's not very useful is because it's creating a ton of delegates here. So anytime that you call something like this, a delegate is being created. And for a very short operation like the squaring of an integer, for example, this is a very inefficient way of doing it. And this is why we have some benchmarking code, so that we can see just how bad the whole thing is. Okay, so now that I have this, we're going to benchmark this particular function. So this is where the benchmarking package comes in. I'll say benchmark here in attributes, and then what I'm going to do is I'll just get the summary as benchmarker. Let's it's actually benchmark runner dot run with the argument of program, and then I'll get the result. So we'll have, I'm going to remove static here, going to make this public as well, keep everything public. So then I'm going to just right line the summary. All right, so this is going to be quite an involved kind of process. Let's actually execute this. As you can see, there is a lot of execution and warm up, and it's generally a very sophisticated kind of product for running the entire thing. Okay, so we can see that the median execution value for square each value is a whole 13 milliseconds. So let's see if we can somehow speed this up. And the reason why we want to speed this up is so that we can avoid those delegates that we're making here. So it's probably easier to just calculate once again some sort of partial sums in between the tasks and then put those in there. So but in addition to that, I mean, the alternative is of course that you can keep calculating them as you are, but instead just partition things differently. Because if we just partition the count into, let's say, 10 buckets of 10,000 items, that's going to be more efficient because we won't be creating so many of these delegates. So let's see if this will actually help, or whether I'm lying to you. So we're going to make another method called square each value chunked. So we're going to make chunks of the overall thing, and there is functionality in TPL for doing exactly that. So once again, I'll copy the first three declarations over here because we're operating on the same values. But then we're going to do something different. We're going to call partitioner.create. Now, a partitioner is essentially the component which specifies how to take your range of values and how to split them. So in this case, what I'm going to say is that we'll make a partitioner which takes the count number of values, but it splits them in groups of 10,000. So we'll have 10 threads at most. And I'll say that this is going to be part. And remember, the partitioner is something that you can actually feed into a parallel for or a parallel for each. So here I can say parallel dot for each. And the first argument can actually be the partitioner. And the second argument can be the range that we're operating on. So for example, we might be operating on items from, let's say, actually this should be no, 10,000. We could be operating on items from 10,000 to 10,999, for example. So or 19,999. So it's all split into these groups of 10,000. So we take a range which is actually a tuple. A range is a tuple of the starting and ending indices. And what we can do locally on each of the threads is we can just make an ordinary for loop. So this is a for loop that can operate starting at the beginning of the range, so at range.item1, and ending at range.item2. And for each of the iterations, we can once again just set the results. So we can set the results at index I to be math.pow I2. And let's cast it to an int once again. And let's actually measure the performance. So once again, I will add a benchmark here. And we can execute. All right, this will take some time. All right, so as you can see from these results, the square each value chunked is a lot faster than square each value. So it took 2.9 milliseconds instead of 13.6. So that's a 6-fold increase basically. So this illustrates how you can optimize the performance of parallel algorithms by using a partition that you define yourself. And of course, it's possible to define entirely custom partitioners which look at your data and create exactly the separation that is the most optimal for a given task.